Hello friends, welcome to our second lecture on electric discharge machining, that is EDM. In my previous lecture, that is in my first lecture, I have covered mainly 3 points, that is introduction to EDM, then how sparking takes place in EDM process and working principle of EDM process. In my today's lecture, I am going to cover EDM system, in that different elements, then dielectric flushing, then electrode, and at last we are going to see the tool wear. So let us move for the first point. So you can see in this figure, that is a schematic diagram of EDM process. There are 4 components are there. One is the power supply, then second one is the dielectric system. So dielectric fluid system is the second part. So it consists of pump, delivery system, filtering system, direct fluid tank. Then third one is the servo system, which gives speed to the tool, and fourth one is the tool and workpiece. So these are the 4 major components or elements of the EDM machine tool. So first we will go for the dielectric system. So dielectric system is the first component of EDM process. So it consists of direct fluid, reservoir, filters, pump and delivery devices. So a good dielectric fluid has the different properties, in that it should have high dielectric strength, so it should not break down easily. So it should have high dielectric strength, so it should remain electrically non-conductive with a very high voltage, high potential applied. So until it's a breakdown voltage, between means it remains electrically non-conductive until the required breakdown voltage between the electrode is attained. Take minimum possible time to the breakdown. So this breakdown, it is called actually ignition delay time. Ignition delay is the time required after its breakdown voltage is achieved. This time required for breakdown of this capacitor, it is called the ignition delay. So this is a good dielectric, should have very less ignition delay time once the breakdown voltage is reached. So after this sparking occurs, the zone actually ionizes, and during off time it should be deionized. So this deionization time should be as less as possible. So deionize the gap immediately after the spark has occurred, and this dielectric should act as a effective cooling method, that is medium. So it should take away whatever unnecessary heat are there, it should take away, and it should have high degree of fluidity. Suppose you want to make a very high length to diameter ratio, high aspect ratio, there in between tool and workpiece you have to flow the dielectric there to continue the machining. So for flowing this dielectric there, direct fluid should have actually very good fluidity. Its viscosity should be low so that it can flow in between the small gap when you are making this aspect ratio holes. So commonly used direct fluids are transformer oil, paraffin oil, kerosene, lubricating oil, or deionized water. So in that deionized water actually it is has certain advantages, which gives high material removal rate. So it acts as a more effective cooling medium, but it has a certain limitations also. It has high tool wear rate. So because of this high tool wear rate, you cannot use this direct deionized water everywhere. So it has corrosive properties also. So this, because you are using deionized water, so if you are using steel, mild steel, so it corrodes. So to overcome this problem, you have to use, or you have to reduce the corrosion problem. So electrical conductive increase and this dielectric constant actually reduces to an unacceptable level. Also, filtration of dielectric before the recirculation, it is required to maintain the fixed dielectric strength. So if the debris, that means the crater particles, are actually, it is in the micro size, so if it is mixed into the dielectric, so its a dielectric constant actually decreases. Okay, so it breaks down with a lower voltage. With lower voltage also it break down. So to keep the dielectric fluid same dielectric constant, to maintain it's a same dielectric constant, this dielectric has to be filtered and it should be recirculated in the machining zone. So there are different ways you can apply for the dielectric fluid into the inter electrode gap. So we'll go for the next point, that is a different methods of flushing. So first one is the suction through the workpiece. So look at first diagram, that is a suction through the electrode. Okay, so in that tool is there, inside the tool there is a hollow. This is a hollow they have used as a hollow tube. So this dielectric fluid actually it is sucked and it totally immersed into the dielectric chamber. So this from tool, there is a hollow tool, this dielectric is sucked there, and from this outside you can see this dielectric is coming into the electrode gap. Now second one is the dielectric can be sucked through the workpiece also. So this is a second option. Now look at third option is that very good option, that is mostly it is used. Dielectric can be delivered through the hollow tube, through the tool. Dielectric can be delivered into the inter electrode gap and it is coming outside from this inter electrode gap. So here through this workpiece also you can flow this dielectric in the fourth option. So through this workpiece also you can flow this, you can deliver this dielectric and it is coming outside from the inter electrode gap. In fifth one option, as I have shown in the figure, you can see dielectric can be delivered through this just a jet flushing. So using this jet flushing technology, through a nozzle you can deliver this dielectric into the inter electrode gap. Otherwise you can do this flow of the electrode, you can flow this electrode dielectric by periodic cycle of electrode. Okay, but jet flushing is less effective, hence it should be used only when none of the other methods can be used due to tool or workpiece configuration. In case of inflammable dielectric fluid, the workpiece should always be immersed in the dielectric fluid to minimize any chance of accidental fires. So this is about the flushing of dielectric fluids, and these are the different methods of flushing. Let us move for the next point, that is a electrode. Okay, so electrodes are the tool and workpiece in EDM process. So it is used for the mean of providing electrical energy to the work material, and the machining accuracy, it is depend on the form of stability of the tool under several electrical and flushing stress condition. It should have wear resistance also. So the ability of electrode to produce and maintain the detail, is directly related to its resistance to wear and machinability. So minimizing corner wear requires choosing an electrode material that combine higher strength with the higher melting point. So what about the desired properties of electrode material? So look at to a desired property, it should have be easily machinable, it should be soft material can be easily machined, so it should have low wear rate and good conductor of electricity as well as the heat. It should be cheap and it should be readily available. So these are the different desired properties of the tool material. So different electrodes are actually used like graphite, copper, brass, copper tungsten, cast aluminum, copper boron and silver tungsten. Out of that, graphite, it is easily machinable, it has low wear rate, high conductivity, but there is a main problem of this graphite. Although it has a low tool wear, but at high surface finish and high material removal rate, but brittleness is the undesirable property characteristic, because of which it is prone to breakage. So it is a very brittle material. So with a very small force also it breaks. So that the main problem of using graphite is prone to the breakage. Another, that is copper, brass, it has a high stability and relatively low wear rate is there. Copper tungsten, low wear rate, although it is expensive but cannot be machined easy shape. Other things are there, cast aluminum, copper boron and silver tungsten. So copper and graphite, based on this all, whatever tool material are there, copper and graphite are the most commonly used because of their easy machinability. Graphite electrode with finer grains, which results in low tool wear rate and which gives the better surface finish and high material removal rate. Now let us move for the next point, that is a tool wear. So first I will tell the what is meant by tool wear. Actually tool wear, it is quantified by the wear ratio, and wear ratio may be vary in the range of 0.05:1 to the 100:1. Okay, so here I have shown in this figure different kinds of the tool wear. So at corner you will get the corner wear, then end, at end wear you will get, then side wear you will get. Okay, and you can calculate the corner wear ratio also by using the mathematical formula, and same you can find the side wear ratio, end wear ratio and also volume wear ratio. Okay, so this is about the tool wear also. Okay, in EDM process. Let us move for the next element, that is a servo system. This is another component of the our EDM system. So it is used to maintain the predetermined gap between the tool and workpiece. There is a gap voltage sensor in power supply which sends the signal to the servo system. As soon as it sends sense the gap between the electrodes and has to be bridged by the some electric conducting material, a signal will be sent to the servo system to reverse its direction. Actually the servo system will keep the tool reciprocating towards the workpiece surface, so that this whatever debris material or debris particle are there can be flushed out and with the direct fluid, and it cleans out the clear electrical conductive materials also. So requirement of the servo system are sensitivity of small movement and enough power to work on the height of the ramp, electrode and flushing forces. So electrode refeeding, to accurately machining, the reduced length must be compensated. So there is a tool wear is there in EDM process for accurate machining. So whatever the reduced length of the tool can be compensated. Otherwise, the length of each successive hole to be drilled will be shorter than the desired one. So in electrode refeeding, the tool after drilling a hole is brought back every time to the reference point where from the depth of the drilling is measured. So there is a reference point is there. So after every drilling, we have to move to the tool toward the reference point, and you have to check how much length of the tool is actually reduced. Okay, so if there is a tool wear rate, is there, then tool wear rate in subsequently machining using same tool, you will see smaller depth of cut. Okay, so reduce that, you have to come, you have to compensate whatever the tool length compensation is there, whatever the tool length is reduced, and that should be compensated. And for that, actually you have to bring the tool into the reference point, and you have to check how much the distance of the tool is actually reduced. So you have to move that exact portion into the workpiece using that tool, so that this exact dimension of the tool workpiece may be measured. So we can use the CNC EDM also, and this there is a CNC EDM. You can move the table in such a way that any complex surface can be made by this EDM process. So you can reduce the tolerances further, and you can increase the accuracy of the tool. Okay, so this is about the servo system. Okay, so in this lecture we have covered the different elements of our EDM system. Okay, then dielectric flushing methods, tool wear. Okay, so here we will stop. Thank you.
Hopefully you might have enjoyed the lecture. Then please do like the video and know your thoughts in comments. Please do share this video among your friends and don't forget to subscribe to our channel. After subscription you can press the bell icon to never miss the notification regarding our new videos. Thank you so much.